Yes, we're back in the room at the Pendle Suite, and taking us up to our next break is a very exciting session all about how to make the best of small hardware encoders in moving devices. Please give a great ComCon welcome to Mr. Tim Panton.
Yeah, no, I'm afraid there are no scented candles to give away, but there may be the odd secret, so we'll see how that goes. This talks about WebRTC on moving devices, and it's actually kind of part 2 of a talk, part 1 of which I gave at Camellia World 2 weeks ago. But that's good because that's already on YouTube, so you could watch that as well. So I'm going to talk about encoders and cameras and small stuff, but I guess I should introduce myself because that's what we're supposed to do in these things. I'm Tim Panton, I'm the CTO at Pipe. Pipe is a German company which makes a secure WebRTC stack, and secure means many things, but I think the most important thing is that it's memory safe. It's written in a memory safe language. And it's basically for IoT devices, and it's in tens of thousands, let's be a bit vague there, of baby monitors around the world. And it has a speciality that it does edge-based identity. But I'm actually not going to talk about any of that, well, almost none of it. What I'm actually going to talk about is moving WebRTC from moving sources. And one of them is this thing. I've got a couple of projects which I think are representative. This thing is a little robot. Some of you may have played with its sort of precursor. It's grown a little since then, but the idea is there's an autonomous driving competition in Berlin every year, and you're supposed to drive these things, teach these things how to drive themselves around a track. And I decided to teach the AI by driving it through the lens. So I wanted to have a live feed of what it could see, and then I would drive based on that and use that to train the data. Actually, it didn't turn out that way for reasons. And as you can see, the first trained thing was really not very happy, and it had an unfortunate time with the competition. So I looked at this, and two realizations struck me, one of which is that it wasn't doing very well. And I got my cloud bill from Google for the training. And then that was the first piece. And then the second piece was I realized that there was a solid yellow line around the track. And I thought, this doesn't look too difficult to write a yellow line follower. So I ditched almost all of the hardware, all of the AI stuff, and lost a ton of weight on this thing, 350 grams worth of weight, and made it a lot smaller, and wrote a yellow line follower. Now, there's still a little bit of AI in it because I asked ChatGPT how to write a yellow line follower, and it came back with an algorithm which actually didn't quite work, but it told me the key thing, which is that it's good to convert it to HSV, because that makes the problem simpler. So anyway, I read from dev video, look for the largest group of yellow pixels, and then steer towards them by driving pins on the Linux interface to the GPIO. And the fun thing is you can do this at 30 frames a second on a Pi Zero, which is kind of cute. Oh, that's open source, by the way, up there on GitHub. But you still kind of want to know what it's thinking. So to tune that algorithm, I want to kind of know what it's thinking. And the cute thing is that reading from dev video, this stuff is just data, right? So you can rewrite it. It's just RGB data. Well, before you turn it to HSV, it is. And so you can just do stuff with it. So in this case, I put the speed of the respective motors down the sides with little green stripes, or red if it's going backwards. And I use an indicator to see where it thinks the target is and where it's aiming for. Paint that bright yellow with a black dot in the middle. And the other thing I could do is to turn up the saturation and the hue and mess with that so that the yellow is really zings out. That's not the actual yellow. And the result was we came second. It does actually work. It worked shockingly well. The reason the other guy won is basically physics. His car was taller, which meant that he could look further ahead without seeing without looking off the track. What we found is if we turn the camera angle up, which is what you'd naturally do, it started chasing people's shoes and other things because they were also yellow. So it's like an angle thing. So that's one project. The other project is actually almost as much fun, which is real-time video from over the shoulder of a driver of a race car to the pit. So the idea is the pit crew can see exactly what the driver can see in real time and talk back. I mean, they've all got radios and stuff, but they haven't generally got low latency video feeds. And so that's the idea, is that they can see what's going on and they can see how badly things are going. That's a screen recording from a prototype, so it's not quite what it should be. And those two projects, they seem quite different, but they actually got some quite common engineering goals, like low latency video, high-ish quality video, low weight, low cost, ease of use. And by me, ease of use, I mean that this isn't the most important thing, right? The video is an adjunct to the main thing that we're doing. So it's an adjunct to the AI, it's an adjunct to driving. It's not the main thing. And so it shouldn't get in the way. It should just like kind of work and not be a nuisance. And then the other thing was that there was like as an element of remote control, an element of sending data to the moving vehicle, either to control it or in the race car cases you'll see, to tweak the camera behavior. So it's worth backtracking about what the other half of this talk said, and that was really about bandwidth and networks, like how do you best make best use of the available bandwidth, how does WebRTC treat networks and stuff like that. The slides for it will be on pi.pe after this event for both of the talks, and the video from Camellia World's already on YouTube. So you ask yourself, certainly in the case of the race car, why this is different from the rest of the media landscape. Like, why is this not just another broadcast app? And the key thing is that we want less than 200 millisecond latency. Otherwise, the conversation with the driver is meaningless because they've already gone around the corner by the time you've talked to them. So that rules out using Dash, HLS, SRT, any of those protocols, because they have typically over half-second latency or more. But we still want it to be broadcast compatible, because although for the moment that goes to the pit crew, you can see that there's potential broadcast applications for this kind of thing. So, you know, we still want to use H.264, and we want it to be relatively low cost and low weight. I mean, this is, I don't know, 300 grams or something. And so we're going to use an ARM SBC, single board computer, but probably run WebRTC on it, because that's kind of what I do. So this is what an architecture looks like. You have an encoder sitting up there reading from the camera, encoding into H.264 or potentially H.265, feeding V412, which is the standard Linux interface, or GStream, or both, or whatever. And then there's a couple of back channels up to control the camera exposure time and to control the bit rate and request full frames in case they're necessary. And then all of that gets sent up or down from the WebRTC stack. And the WebRTC stack is also talking downwards to the GPIO in terms of like getting control, sending control messages, and getting sensor data potentially from the device. And then it talks signaling over the internet, obviously, but actually you want to keep your latency down. You want to keep the thing local-ish. Now, I've totally cheated in the demo later. I did have a 4G. In fact, I do have 4G, but the 4G in here is simply terrible. So I've gone for a very local LAN of an Ethernet cable between here and my laptop, which is, I admit, totally cheating, but it kind of, I want it to work. So, and then the end result ends up on a laptop browser, ideally. So a sample device for these SBCs, and this is like, I have servers that have got lower performance than this, right? This is 8 cores, 8 gigabytes of RAM, 32 gigabytes of disk, like on a board that's, you know, well, it fits in that box, right? And it's got external antenna connectors, and the amazing thing is it's also got an M2 slot. So you can put like your SSD in there, or you can put a 5G card in there. It runs Ubuntu, and the whole thing, actually, it says I'm claiming it weighs 185 grams. I think with the antenna and the battery, it's a bit heavier than that, but it's kind of order. And the whole thing draws 15 watts at most. And, I missed the top thing, 4K, 50 frames a second of H.264 at 15 watts. Like, you try that with an NVIDIA. So the other device, which is kind of the other end of the spectrum, is like $10. Again, H.264 at 720p, 30 frames a second. For Pi Zero, you only get one ARM core. You only get half a gig of RAM. You don't get any disk apart from SD card. The Wi-Fi antenna is on the PCB, although you can cut it and solder it and do stuff. And the I/O possibilities are limited to USB 2. But it's running Debian, and it's cheap, and it's light. I mean, even the robot you saw before was 400 grams, including the motors and batteries. So the Raspi camera, there are 3 official cameras. There's a Pro camera, which takes a nice, chunky lens, which is a little heavy, but like it's a proper lens mount, and you can get other lenses for it and whatever. There's a standard one, which is autofocus, but it's all right, and the resolution's quite good. And then there's this Pi Zero camera, which is a much smaller lens and a lower resolution, and it's a little bit crappy, to be honest. And then there are a ton of third-party ones, although these cameras tend to only work with the newer OS or with driver patches and stuff like that, so it's like a little bit messy, and not all of them talk well to the H.264 encoder. So this game gets a little more complicated if you stray off the main path. The hardware for the Raspi is well integrated with V412. Now, V412 is this kind of Linux interface to video, which does the most amazing things. There are knobs you can tweak for brightness, contrast, color, all of that, and it's for free. Like you don't put any CPU into doing this. You can flip, sharpen, all of this, click a thing, and it does it with 0 cost on the CPU, which is astonishing. And likewise, the hardware 264 encoder is manageable in the sense that you can set the bit rate and the quality and the full frames on demand, on the fly, during a conversion. You can't change the profile and level whilst it's running, but still pretty impressive what you can do with it. So the pros are that it's cheap and there's a ton of cameras. The cons are there's limited frame rate and resolution, and the I/O is, frankly, hugely limited. And the big thing that stops us from using them is limited supply. You can't always get a hold of them, and I have a little stockpile, but that's not really the point. So the other place we looked is these Vim devices, and the nice thing about them, well, the nasty thing is there's only one supported camera, and it's quite expensive, but it takes an M12 lens, which is a security camera lens. It's this lens that you can see on the front there, which is quite light, but it's got a range of lenses, and there's a nice things you can do with it. Good sensor. The cable is appallingly fragile. You really have to protect it. If you flex it too much, it just snaps. And some of the tweaks we talked about for the Raspi do exist, but not all of them work, and not all of them work in the right order, and like there's sequencing problems and stuff, and some things. And likewise for the H.264 encoder, in theory, it's controllable, but in practice, V402 and GStreamer is not exposed at that level, so you can't do the stuff that you can do with the Pi, which is a shame. So yeah, pros and cons, good lens, good frame rate, good resolution, it's available, you've got an M2 slot for great I/O, like 5G and whatever. And the disadvantage is that the software support is, like, you haven't got the huge Raspi community, so it's a little patchy and very Chinese. And the camera cable is appallingly fragile. We've got through more cameras than I like to think about. So there are a couple of Vims, and the Vim 4 has support for H.265, which we thought seriously about using, because you get lower bandwidth for the same quality, or higher quality for the same bandwidth, whichever you want to play it. But it turns out to be almost unusable, because you end up to have to pay $1 to enable it in Edge. It's not supported in Chrome at all yet. I think it's in Canary behind a flag. And It's supported in Safari, but only behind a flag. So actually, and realistically, it's not available on any normal person's browser. So then you'd be building an app, and it's like, well, I don't want to build an app if I don't have to. So we went for the Vim3 and a 3D printed case, and that's like actually not this case. It's the case that we really used. So you can see the camera and the Vim and the 4G card and the SIM card and the other interfaces. So what we ended up with, as I say, is Vim3 Basic, a daughter card with the SIM on it and the 4G module, the camera, and big thing here, antenna connectors which connect to the top of the car. So as you'll see in a minute, that turns out to be really important. So one question people would ask is like, well, why didn't I use a phone? Like, why am I bothering with all this hardware? Why don't I just stick an iPhone on the front of the vehicle? Well, one of them is partly because we want to look over the driver's shoulder, and the other one, the thing is that you then need an external antenna, because these things are pretty much Faraday cages, as you'll see in a minute. And the other thing is I wanted to control over the lens. We wanted to be able to put whatever lens in we wanted, and that gets pretty difficult on there. And the other thing is it's a fantastically hostile environment for a big sheet of glass, which is basically what phones are these days. So we took that camera and we installed it in this car. I must say I was like knocked sideways when I was sent this video, because I didn't actually install it. And there it is, sitting there next to a horrendously expensive live video camera for broadcast. But anyway, so that's installed. I'm all excited. So we switch it on, and the results are terrible, like really bad. There's a ton of problems. The colors are wrong for a start. It's like, how does that happen? Exposure's wrong, the field of view's wrong, the latency's too high, the bit rate's wrong. It's like, so we work through, as you do with these things, you make a list and you slowly work through the things, like fixing them. And this one was great. This is my favorite bug. Like, we'd mounted the camera, as it turned out, upside down. So we flipped it by using a V412 flag, which just flips the image, like vertical flip, no problem. Unfortunately, the way the driver does this also resulted in the RGB being swapped. So it was no longer RGB. So we moved the flip into a GStreamer pipeline. I mean, heck, we've got 6 spare cores. We might as well use them for that. So that fixed that problem. And then the exposure, as you can see, it's like the actual outside the windscreen was whited out. I'm going to try and demo that later, but it's probably not going to be it's not bright enough outside for it to work, but we'll see what happens. So we used the V402 switches to disable the automatic exposure control and the automatic gain control and the automatic white balance. I always struggle with the acronyms. And manually control the exposure, so we can manage the exposure to meet the situation that we're in, and then we can tweak it so that it wants what we want. And the fun thing is we can send those V4L2 commands over the data channel live, so we can see what it looks like and then send those commands. The other thing that we had a problem with was the field of view. Tried to get V4L2 to trim the field of view and failed miserably. And I have no idea how it's supposed to work, but I couldn't get it to work. So we ended up, again, using a core and getting GStreamer to crop it. And the other thing we did is, because it's a swappable lens, we found a lens with a narrower view. And that was kind of nice. And we ended up, because we'd done the cropping in GStreamer, we went down from 1080p to 720p, which actually lowers the bit rate. I mean, obviously lowers the perceived quality to some extent, but we think it's a decent trade-off. So the end result, and the latency, yes. Measuring latencies, and glass-to-glass latency is an interesting challenge. Turns out the easiest way to do it is to put a clock on your screen, point the camera at the clock, watch the camera feed the video on the same screen, and take a screenshot, and then subtract the two numbers that are next to each other. And the net result was 230 milliseconds. If anyone's got a less annoying way to do that, I'd love to hear it. Yeah, he does something with QR codes. Yeah, I'll look at doing that, but I don't think that's pure glass. Anyway, whatever. So we got it down to 230 milliseconds, which is kind of nearly good enough. No, and here are the sources of it. And I think the one that we can get most joy out of is around the 4G and internet queue. We're still like, we can tweak the ends, but the middle, I think, moving to 5G and potentially tweaking the driver queue, we might be able to get that down by another 50, 100 milliseconds if we're really lucky. So, bitrate. Bitrate is the big thing here. So the hardware encoder is capable of changing the bitrate on the fly, like it's in the chipset. And it can also generate full frames on demand, which is a thing you really want for WebRTC. Like, best use of WebRTC is to only send full frames when they're essential, and maybe every 20 minutes. Like this 2-second keyframe stuff, it's a huge waste of bandwidth. And you're wasting quality, basically. Unfortunately, neither of these encoder features are exposed in the V412 API or GStreamer. I mean, they are on the Pi, so the features are there. They're just not enabled in the implementation. But the library that the GStreamer plugin uses is open source, and it does talk to the encoder. So an ugly hack was born. So I have some excuses. I mean, it genuinely is ugly. And one of the things was I actually literally couldn't find the source for the GStreamer plugin. Like, it must be there somewhere, because I think they're obliged to make it public. But I could not find it. And anyway, frankly, I'm scared of rebuilding GStreamer. It's like, it's a labor of decades' work. Or, no, that's unkind. But I really didn't want to if I didn't have to. And I wanted the lowest latency, so the idea of going through several levels, up through GStreamer and back down again, seemed like a little bit of a waste. And so I thought, like, particularly for the generating a full frame, when you need a full frame, you need a full frame. And you want to minimize the time it takes to request it. So the fact that I already had a bug to fix in the encoder low-level library anyway, because there was a thing it did, it lied about whether it was NV12 or ARGB at some point, and so I had to go and nail that down. So I had to change that library anyway, and I thought, well, okay. And our WebRTC stack, Pipe's WebRTC stack, is in Java, memory-safe language, and JNI is absolutely horrible, so I didn't want to talk to the encoder direct from Java. So I'm like agonizing for a bit, and I come up with this hack, which is, again, open source because it's based on their existing public encoder libraries. And it basically doesn't touch GStreamer, and it just does things to the encoder library. And what it does is it maps a 2-byte file into memory, both in the Java WebRTC stack and in the encoder library. And then the WebRTC stack writes to those bytes when it wants to change the bit rate or enforce a full frame. And the encoder, every time it runs to encode a frame, it checks those flags. And there it is. Now, if Sandro was in the room, which thank goodness he isn't, he would point out that there are 2 fairly ugly C errors in this, but well, not errors, but risks in this. But fortunately, he's not here, so we're in the clear on that one. So this is actually not public. Well, it is now, but like the rest of it, the underpinnings of it are not public. But what's cute about this is that this is 2 completely separate languages sharing a 2-byte file for controlling an encoder, and it kind of worked shockingly well. Yeah, so it worked. And you can, well, it's actually not changing. You can see the actual bandwidth changing. That's the consumed bandwidth. And you can see the available bandwidth tracking and then the target bandwidth tracking with it. Turns out that behavior for WebRTC trying to manage the bandwidth doesn't work that well in this environment because people don't like the perceptual changes that are involved in that. So we we found that there are some UX, once we'd done that, we found there are some interesting UX things, which is that the pit crew didn't like the quality changing. They were much happier with it being the best we can do for this circuit and then just leave it there. So we basically didn't allow WebRTC to do dynamic tweaking. We would play with it, get to a good level, and leave it there. And the other thing that we found was that a classic thing that Chrome does is if it has lost a packet a while ago and it's asked for it back again and it finally gets it, it's now got maybe 10 or 12 frames to play out. It plays them out in a hurry. And if you're in the pit crew and you're watching your driver and he appears to be accelerating into a corner, like, what? What's he doing? Well, actually he isn't. It's just Chrome catching up. Right? So this is a bad thing, and we try really hard to stop it from doing that, which is basically keep the jitter buffer really small, and any knacks for frames that are more than a frame behind, just forget it. It's like not happening. And so that was like we're not a video conference app, basically. It's not a conf call. And speaking of things it isn't, why is this not WIP? Like, why am I not using WIP for this? And there are actually two reasons, one of which is that WIP is a lovely standard, it's great for this kind of thing, except that it's not peer-to-peer. It's very much client-to-server WIP. And I don't need a server in this. I want to stay on network. If I've got a private 5G network, I want to stay on it. I don't want to transit everywhere else if I don't have to. And then the other thing is that the WIP doesn't support the data channel, and we want to use the data channel for sending control messages and getting data from the device. So what kind of data? Well, yeah, we want to control the camera with setting the bit rate manually rather than using the RTCP tactics. We want to manage the exposure. We want to control that and maybe even change it minute by minute. We want to monitor the sensors that are available on the camera, which is things like, there's a temperature sensor in here. I wonder if it's running warm yet. Yeah, it's just warm to the touch. And there's a G sensor in there, which is kind of cute. I haven't actually seen that live yet, but it should be fun to watch it going around corners. And then we also have the data channel for management. So I can do remote access. I can shell into one of these cameras, even if it's on a 4G network, through the existing WebRTC security relationship, essentially, and the NAT traversal and all the other things. I can end up sending a shell over the data channel. And even more fun, I can send an update. I can send a new version of the app over to the camera and then tell it to reload and use that camera, which is scary, but it's actually really convenient. It's much easier than getting it unscrewed from the car and somebody plugging in a cable and all of that stuff. So I'm going to now do a series of high-risk things, as usual. So this, with any luck, let's just reload it and make sure it's live. Yes, it looks like it is. Right, so let's make this as big as it goes. Right, so what we've got here is a camera. And I'll turn the G sensors on so you can see that as I tip it around, the dials at the top move around. The temperature is just over 50 centigrade. And there I am. And of course, if you don't want to see the dials, you can do that. And you might notice that it's a little bit grainy. So what we can do is say, hey, we can turn the quality up because we've got. Now I'm cheating because I'm using this Ethernet. So hey, we can whack the quality all the way up like that, and yeah, we get better, less grainy, quicker transitions, that kind of stuff. So the other thing we can do, and I don't know if this is going to be. Well, the sun's almost coming out, so it might be noticeable, but it might not. So we can do this thing I said about the exposure management. So at the moment it's on auto expose, but let's say it's turned off auto white balance, but it's still running at the same exposure as it was before. And now I can tweak the exposure. So maybe I'm going to turn it down a bit. Okay, that's not much different. So, weirdly, it's, well, we can try it in a second. So I can turn it right down like that, and as Sam says, maybe I can turn it at the screen, but we get these weird moire effects because we're now, this is sampling at like 28 frames a second, and that's probably at 26 or something, I don't know. So we get a weird moire effect, but it's a thing. But anyway, so we can manage the exposure like this. Oh, and yes, of course, I can full screen, although actually this screen's so big that I can't fill it. But yeah, so this is actually quite, close, decent, real-time-ish sort of thing. And the other thing I'm going to do, since I have a minute or 5, let's see whether we can do the same. I can do a better demo of the exposure thing. So this is a camera that's sitting on behind my super messy desk. With any luck. Right, there we go. So this is my super messy office, stacks of old paper. But the interesting thing is, out the window, you've no idea whether that's a cloudy sky or not, right? But if I now turn the auto exposure off and right down, you can see that it is actually a cloudy sky, and there's a big bush outside that door. So that's the kind of difference that we can make with controlling the exposure remotely, which is kind of cute. And I will also do a remote shell, maybe, into, so home or here, which one do you want a remote shell to? Home. Home. Let's go to home. So this, of course, is not. Oh, it does work. There we go. So I'm remote shelled into one of these that's sitting on my bookshelf, and I have no idea what the NAT traversal was like for that. I've genuinely no idea, and I don't care because that's WebRTC. So, and I won't push a new update because that would just break things. So, yeah, I think that's the demo done. So the takeaway thing from this, I think, is that, basically this is something that only WebRTC can do. This is a peer-to-peer, low latency, live video. And you can do all your muck and your web transport and all of that. And yeah, they can't do this. There's no server involved. Well, all right, there's a signaling server, and maybe if you're on a bad day, there's a turn server. But there's no server involved. And I can deploy this on, if James had got his 5G and I had one of his SIMs, we could be on 5G on this, running on a private network. And no, I wouldn't have to change a line of code. It doesn't care. It works this out for you, which means that we can go from track to track without having to think about this stuff too much. Because that's the other thing that I realized of this, is that these guys turn up at a track, and they go to Monza, and they need to be working within an hour or two of unloading the car from the trailer, right? So it has to work there, and then they take it to Nuremberg or wherever, and it's a different environment. It's probably a different damn carrier, but it's spotty 5G or spotty 4G, and the cars are moving quickly. So it's a really interestingly challenging video network for trying to get video over. But we seem to have got something that's usable, which is really nice. And so, yeah, we're enjoying it. So, thanks if you've been listening. I'm a little bit deaf, so if you've got questions, you might need to shout them. Contact me on either of those. I've kind of given up on Twitter, so you can tweet at me and I might read it once a month, but that's about as often as I get around to it. That's the Mastodon that I'm on most days, which is good. And then I'm doing consulting obviously on Pipe, but also on open source WebRTC and kind of anything else that looks interesting that people might want me to do. So I'm going to put this back to the camera because it's you know what? I'm going to do something really stupid.
It wouldn't be the first time, Tim, wouldn't it?
It absolutely wouldn't. It absolutely wouldn't, David. So I'm going to do something really stupid, and we're going to see how bad the 4G is here. So let's do that and reboot it onto 4G and see how that turns out. Right. Whilst that's rebooting, questions?
Yeah, I would just like to tell you that actually you've heard of Dangerous Demos. Well, Tim is really a founding member of the Dangerous Demo Club.
Yeah, I'm sort of like, I'm not sure I like this image, right? Like, there's a sort of bunch of people who think that nothing I do is reliable or safe.
I just always like the number of stages that there are in your demos, that this is connected to that and that's over that network. Excellent. Who's got a question for Tim before we warmly thank him? We do have time for one question before the coffee break. Yes, sir. Yes. In fact, there's a microphone coming to you. Thank you, sir.
Why don't you use USB cameras? Is it because the latency? You could have the USB camera pointing, mounted in a place where it should be, and the box somewhere hidden underneath.
Yeah, I think we probably will use. I think where we'll end up is having two cameras. I think we'll end up having a USB camera pointing backwards, like the rear view, and one pointing, and the built-in camera pointing forwards. The data path is shorter, and those V412 tricks, they kind of mostly don't work over USB. So some of them do, but you've got another kind of 2 or 3 layers between you and the camera hardware. Whereas this, if you get it right, the encoder is talking very close to the camera. And so there's less, oh yeah, well, we're connected, that's interesting, and it's actually working. Yeah, so it's like partly latency, but also largely about being close to controlling it.
Thank you. I'm going to not take any more questions now because we're going into the coffee break, but Tim is here for the whole deal, so if you'd like to approach Tim, please feel free to do so. We've got about a 20-minute break, and then we're back in this room for a case study of a cross-platform video conference that at least involves Matrix and Jitsi, if not PeerTube as well. So all the fun of that is coming in 20 minutes' time in this very room. In the meantime, on the Wi-Fi, let's give Tim...
This is on 4G. Vodafone 4G we've got here.
In that case, let's give Tim Panton an even bigger ComCon applause.